Okay, now we already done with the bipolar transistor. And today will be, next one will be another one, what we call a JFET. Okay. And both will be the same. That means the first thing we want to learn more on the JFET, and the first part will be DC bias. Exactly the same bipolar transistor. You have to get the DC bias first. And the next one, you get the bipolar for amplifier. And you get a CE amplified, CC amplified, and CB amplifier. Okay? And now the JFET will be the same thing. After we get the bias, then you can get a common source, common drain, and a common gate amplifier. Okay? So the JFET got the Johnson field effect transistor. A type of FET that operate with the reverse bias PN junction. That means still get the diode. Okay. To control in a channel, depending on their structure. They FET form either of two category, N channel and P channel. Okay, first thing, this is the N channel. Okay, this is a symbol, exactly like bipolar transistor. You see the symbol recognize that a NPN or PNP. And same thing, this is a symbol. Okay, for N channel, and this will be a symbol for P channel. Okay, and basically you can get the drain. This is the gate, and this is the source. Okay, now if you're looking into that two symbol, how do we recognize N channel? How do we know this here N channel? Who knows? Let me know.
The arrow on the gate is pointing inward.
This is the same gate, right? But what I asking you, if you see the symbol, how do
The
we know?
arrow on the gate is pointing inward. The arrow.
Exactly. You can see this is the gate arrow pointing for N channel. And this is the gate arrow pointing out for P channel. Okay, the thing when I asking you, you have to answer me if you want to keep going. Okay? You have to follow it. Okay? And now you can see another one. This is the N channel. This the channel here. Okay. P-type, N-type, and P-type, N-type. Just look like you get a diode. Okay. Same thing. And that will be P channel. So that will be a channel. That will be P. And that will be N. Okay. That's the first thing we have to recognize that. Now, DC bias for N channel. JFET. VDD. That's a VDD. Provide a drain to a source voltage and supply current from the drain to the source. That means they will be supply power, okay, for the current from the drain to the source, okay. VGG, that means the voltage here. Set the reverse bias voltage between the gate and the source, okay. Basically, here you get a diode, okay. This side will be negative. The other side will be positive. The JFET, you only operate with the gate source PN junction reverse bias. Okay. Now we'll see in here reverse bias of the gate source junction with a negative gate voltage produce a depletion region along the PN junction, which extends into N channel and thus increase resistance by reducing the channel width. Okay, first thing you're looking on that picture here. You get that a VGG negative voltage, and they connect to the DMM. And the other one, they using DMM connect the current, okay, from the positive to the negative at the drain, okay. So this is the channel, okay. Electron will be moving in this channel. So if they wider, more electron, more current, okay. Narrow, less, okay. If you see here, when you get the VGS, okay, more negative here, and also you can get the current ID, okay. The other one, see the difference. If you get more and more negative voltage, so now the channel will be narrow, smaller, so less current flow. And that's why they prove for you here, okay? This monitor the VGS voltage, and this monitor the current ID. So when you see more VGS negative, the current ID will be less, okay? They say greater VGS narrow the channel between the wide area, which increase the resistance of the channel, and that will be decrease the current ID. Okay? And this is the IC in the lab. Okay? And they're telling you what pin will be the gate or the drain or the source. Okay? So basically in this case, you can see the VGS that will be control the channel, make the channel wider or narrow. Okay, that will telling you more or less the current ID flowing from the drain to the source. Now on this one, let VGG, that means the voltage here will be let widen the channel between the Y area here. That means it will be wider. Okay, that only telling you will be more electron moving. Okay, that will be more current flowing from the drain to the source. Okay, which decrease the resistance of the channel, and that will be increase the current ID. Okay, for this JFET here will be controlled by negative voltage. Okay, more VGG. Okay, that telling you let current flow. Okay, let voltage VGG current will be flowing more. Okay, we'll see. JFET with VGS equal 0. Now they connect to 0, not the power supply. Okay, and they will be given you the schematic statistic of the drain. Okay, JFET with VGS equal 0 and a variable VDS. Okay, so basically at this point, IDSS ID, current ID 0. Okay, at this point also VDS equal 0. Okay, when you try to changing, okay, you can see at the beginning the current will be going, okay, going up. When they get to the point B, you going down. You see what they telling you. This is a VP, ping off voltage. That means at a certain VDS equal VP, then the current at the point B. Okay? And that current will be telling you the value will be IDSS. Okay? And when you increase the VDS, okay, you increase the VDS. Okay? At the IDSS, they say VGS equal 0. That means they're right here. Okay? So, in this from VP, that means from this B here to C here, they say JFET get the constant current. That means the current is not changing anymore, and they will be equal IDSS. Okay, and at this point, VGS equal 0. Okay, and now if you want to increase more VDS, you get into the breakdown, no more. Okay. However, from the current ID equals 0 up to that point B, they say this is the ohmic area. That means you can using the JFET like resistance. Okay? So when the current increase up to the point VGS equals 0, okay? That's what we're talking about. Current of the JFET will be constant. And they will be equal IDSS. And the IDSS, that's the current given by the manufacturer when they build the JFET. Okay? And VGS equals 0. Make sure you know the current ID will be equal IDSS. Okay? Before you get into the VP, they call a peak off voltage. Okay? Then the area here, they can using JFET as a resistance. Okay? So if you get a question, go ahead, okay? Now, we see what here. The maximum drain current out of the FET occur when gate source voltage equal 0. That means VGS equal 0. Then you get the maximum current. And that current will be IDSS. And this current they given to you when they build the JFET. We cannot make it up. The drain current is almost constant in the region between VP and VDS maximum. That they're telling you here. That means from VP to VDS maximum, the current on the FET will be constant and equal IDSS. If the drain voltage is too large, the JFET will be breakdown. Okay? JFET act like current source when it's operating along the almost horizontal path of the drain curve between VP and maximum of VDS. The minimum voltage of VP equal ping off voltage. Okay? VP, that's a ping off voltage. The maximum VDS equal a breakdown. That's already telling you. Minimum VP here, okay? That's a ping off voltage. And the maximum of VDS, that's a breakdown voltage. Okay? Between the ping off and breakdown JFET act like current source. Okay? The value will be IDSS. Okay? IDSS stands for current from the drain to the short width short gate. Okay, that means it's a very just a definition, and you have to know, have to memorize it. Okay, again, between the ping up and breakdown. Okay,
Sorry, I had a quick question.
yeah,
When
go
you're
ahead.
when you're saying there's the breakdown voltage, are you saying that's basically the cutoff region, or is it acting like a Zener diode where there's a breakdown voltage?
They're telling you at that point you can maybe you can cook the JFET. They
Okay.
not they not allow any voltage after breakdown.
Okay.
Okay. Like if I said, okay, what is the IDSS? Then you have to say, okay, IDSS stands for the current from the drain to the source with VGS equals 0. Every time, if VGS equals 0, then the current ID equals IDSS. And again, that's a maximum current. However, that they given to you, okay? When they build, they said they can carry you 10 milliamp or whatever, okay? Ohmic region, the almost vertical part of the drain curve equal ohmic region that equivalent to the saturation region of bipolar transistor. Cutoff voltage. The value of VGS that make ID approximately equal 0. That's what we call cutoff voltage. Cutoff voltage, that means ID equal 0. JFET must be operated between VGS equal 0 and VGS off. Okay? Comparison of ping off and cut off. VP is the value of VDS at which the drain current becomes constant and is always measured at VGS equal 0. If you're looking into here, you can see at this point here, okay, VGS will be 0. So that's why you can get maximum current, and that will be IDSS. VGS off and VP are always equal in magnitude, but opposite in the sign. Okay? That means at this point, VP, okay, and also VGS off, they will be same thing. However, they have to be opposite. Okay? If VP positive, VGS will be negative. And if VGS positive, VP have to be negative. So that will be given by the JFET. Okay? However, they given only one value. If they were given you VP, 5 volt, then you have to understand VGS off will be minus 5 volt. Okay? VGS off and VP are always equal in magnitude, but opposite in sign. And they telling you that sheet usually will given either VGS of or VP. That will be, they're telling you, if I given you what the value of VGS of, then you have to know what value of VP, okay, and reverse it. Given you VP, then you know VGS of. Only thing is, they must be opposite. Okay, now you can see this is almost the same like bipolar transistor you already see before. And now you can see that stand for ID. Okay. And this will be stand for VDF. Okay. And now what is it here? They given you VGS equal -4, -3, -2, -1. VGS equal 0. Okay, so that will be telling you if you get a certain point right here, point Q, what the VGS equal. If I get a point here, I say Q point, what VGS equal?
-1 volt.
Right here. Right?
Right, it's -1 volt.
-1 volt. Okay. At this point, if you want IDSS, you can go here to here, IDSS. If you want to know a VDS, from this point you're going down. So basically, you can change the Q point anywhere in here. You can get the value of IDSS and VDS. So this will be telling you one thing. JFET will be controlled by VGS, right? The thing is, different VGS, you get a different current ID. You get a different VDS, okay? That will be just telling you. JFET will be a voltage device, voltage controller. Okay? That means you changing the VGS. You get a different current ID and a different voltage VGS. Remember, JFET is voltage controller. However, on bipolar, we already know bipolar is a current controller device. That means in a bipolar, you change the current IB, you can change the current IC and VCE. Okay? That is the difference between bipolar and JFET. Now we see what's going on here. You can see at this point, you don't see any channel. Okay? Look like they off, right? So what they say, add cut-off voltage, VGS off. That means they try to get more negative. And no channel, no current flow. So that's why when they measure the current ID, you say 0 amp. So make sure JFET at the VGS off, then you have a no current of ID. That's what they summarize here. At cutoff voltage, ID equals 0, and VGS equals VGS off. Okay, this is a basic operation of P channel. It's the same as N channel, except that P channel requires a negative voltage. You see that? And that will be positive. The opposite with the N channel. Okay? That's what they let you know. We emphasize on N channel. Now, example. For the JFET circuit so they given to you VGS off equal -4 and the IDSS equal 12 milliamp. They say determine minimum value of VDD. That means they're looking for what VDD wanted here. Okay? Required to put a device in constant current area. Okay? Now see what the solution. You have to go through in order you can understand. They say since VGS off equal -4 volt, then you know VP equal 4 volt, correct? We already telling you VGS off and VP, they will be equal the value and opposite. So that's why manufacturer given to you only one. In this case, they given you VGS off equal -4. Then you know VP have to be 4. The minimum value, okay, of VDS of the FET to be in its constant current area. That means VDS equal VP. In the constant current area, VGS equal 0. Given to you ID equal IDSS equal 12 milliamp. The drop across the drain resistor RD. That means they calculate the voltage drop across here. Okay, VRD equal ID times RD. ID equal 12 milliamp. RD 560 ohm. They given to you 6.72 volt drop here. Okay. Apply the Kirchhoff law around the drain. Okay, that means the law here. Okay, you can say VDD equal VDS plus VRD. That will be telling you, okay, the voltage VDD equal the voltage drop across VRD plus the voltage drop VDL. Okay, that means 4 volt plus 6.72 volt. So they will require 10.7 volt for VDD. Okay. Now, next will be JFET transfer characteristic curve. Okay, for N channel. This is the VGS of here, negative voltage. Okay, 0 here. That means at this point, ID 0, VGS 0. Okay, so at this point here, okay, VGS off. Then if you're looking for ID, they will be 0. Okay, and at the point maximum current IDSS. Okay, at the IDSS, what VGS equal? VGS equal 0. So this curve, okay, they're going to transfer characteristic curve for N channel. And they explain to you ID 0, VGS equal VGS off. That means at this point here, ID will be equal 0. And at this point IDSS here, VGS will be 0. Okay? Now we'll see what else. Okay, you know that IDSS. Okay? And this is the VGS off. Okay? So, example when VGS equal minus 2 volt. Okay. Right here. VGS equal minus 2 right here. Sorry. Right here. Minus 2 volt. Okay. Okay. VGS equal minus 2. Then ID equal, okay, 4.32 milliamp. That means this one right here. Okay. At that point, you want to get the VGS, you're going down, minus 2. And if you want to get the current ID, go to the right, you get 4.32. So on this curve here, okay, if you get VGS, then you get ID. Okay, and then that coming up with a formula. This is a formula to calculate the ID. Okay, ID equal IDSS times 1 minus VGS over VGS of square. That's the formula you needed to know in order to calculate the ID. If they given IDSS, VGS, and VGS off.
Mr. Van,
Yes, sir.
the VGS off, where is that on the graph?
Minus 5 volt.
Oh, minus, so VGS is all the way at the extreme end of that graph. The minus 5 volts, okay. And then the last thing is, so IDSS is 12 then, correct?
All right.
All right, thank you.
However, you can see the curve cut the VGS in right here and at this point. Okay. If you want ID, you go to the right. 0. You see that?
Mm-hmm.
And at the point IDSS here, if you want to know VGS, you're going down. 0. Okay? Any point on the curve, they can give to you the value of VGS and also ID. Okay,
So in that formula, ID would be 12 milliamps, and then VGS is -2, and VGS off is
-5.
-5. Is
Yeah,
that correct?
yeah.
Okay, thank you, thank you.
Okay, now the partial example. Partial data sheet for the JFET indicate that typical IDSS my 9 milliamp and VGS off -8 volt. Using this value, determine the drain current ID. They want calculate the ID. For SVGS equals 0 and SVGS equals -1 and VGS equals -4. Okay? So you just quickly go through that and telling me, can you understand for K number, A number, B, and number C? Okay, you have to go through that at A. They given you the ID equal IDSS equal 9 milliamp. It's a correct or no?
Yes.
We already telling you. Okay. At VGS equal 0, then ID equal IDSS. That's why they get 9 milliamp. Number 2, they given VGS equal -1 volt, and you want to calculate the ID. Now, what you have to do, okay, using this formula, try to see how they do calculation. The thing is later on, you have to do whenever you need to calculate the ID. The answer will be 6.89. You can try to see, can you get that the same answer or not? Remember, the FET transistor very, very important. Okay? They come after the bipolar transistor. Okay? So you have to try to understand at least the basic. That's what we're talking about. If you get the answer, same thing they get, 6.89 milliamp. Now you try for me. The last one, okay, VGS equals minus 4 here, using the formula, and do the calculation and telling me you get that answer or not, 2.25 milliamp.
Yeah, I got the same answer.
That's good. You see, that's not hard to do if you understand what is ID, what IDSS or VGS, VGS off, then the calculation will be not a problem. Any question up to this point? Okay, if we can see if you understand it, follow it, that means really good to me. Okay, now in here, they say the forward transfer conductance, GM, is the change in the drain current for a given change in VGS. Okay, basic definition. Gn equal delta ID divided delta of VGS. The unit of GM is Siemens. Data sheet normally given the value GM at VGS equal 0. Then you can calculate the GM at the following. Now you get next formula. GM equal GM0 times 1 minus VGS over VGS off. Okay. If normally they given you the GM0, my question is, what is the GM0? GM0, that means GM at VGS equal 0. If they not given GM0, then you can use formula GM0 equal to 2 times IDSS divide VGS of. However, VGS of have to be absolute value, no negative. Okay, so that's what you get, GM0. So up to this point, you get 3 formula. One formula to calculate the ID. Next formula to calculate the train conductance, GM. And in the GM, they're using GM0. What is GM0? GM0, that means GM at VGS equal 0. Normally given by manufacturer. If they not, you can calculate GM0 equal 2 times IDSS divide absolute value of VGS off. Example. The following information is included on data sheet of JFET. Typical. They given you IDSS 3 milliamp, VGS off minus 6 volt, YM0 5,000 microsiemens. Using this value, determine forward train conductance GM for VGS equal minus 4. So you're using the GM equal GM0 times 1 minus VGS over VGS off. And they calculate the given you. GM equal 1667 microsiemens. You can try to see you can get that answer or not. Okay, and also they want you to calculate the ID. So go ahead and calculate the ID also. Make sure you can get the answer like they did it. Make sure you have to do it, okay? And you can verify for me. Try to more active, okay, in the program. Okay, who get the GM correct?
Got the same answer.
Okay, how about ID?
Yeah, I think so.
Okay, that's good. Okay, and next one, they said certain JFET, they given you IGSS and VGS, and they want the input resistance. This is the formula. If you get the input resistance, you take VGS divide IGSS, absolute value. And the way they do calculation, they given you 10,000 mega ohm. That's not a big deal. Okay, next. JFET DC buyer. Okay, they say many techniques can be used to bias JFET. In all cases, the gate source junction is reverse bias. The most common bias technique, first one, gate fixed bias. The second one, cell bias. The next one, voltage divider bias. That's what we emphasize. That means you want to calculate the DC bias. You get three ways. Supposed to be 4, but we emphasize on only 3. First, what we're going to fixed bias. The second one will be a cell bias. And the next one, voltage divider bias. Now we see. This is the first one. Okay. Showing you. Okay. A gate bias. On the figure B. Okay. Same thing, but they're adding the signal coming for amplifier. What they try to bring it up for you. I want to ask you, if I get -2 volt here, what the voltage at the base?
Is that still -2?
Okay, you say -2. R, G here, I given to you 10 mega ohm. So at this point,
The current is, I mean, the resistance is so large that there's no current flow, so it's still -2.
you get it. Okay, now you get the -2 here. And the resistance is too big, no current flow. That means no voltage drop across that resistor. So the voltage on the other side will be the same thing. Okay? You see that? If you don't have this resistance, it's okay, right?
Yes. Hey,
The
Mr. Pham, a
voltage will be the
question.
same. Okay?
A question, Mr. Pham.
Yeah.
When you have a big resistor like that, is that resistor so big that it's almost acting like a wire? That's why it's -2 on both sides?
Yeah. That means the voltage on this side and the gate will be the same.
But that resistor is almost like a wire because it's so big.
Yeah, so break that means no current flow.
Yeah, okay, thanks.
However, my question will be, you can see you can get a no resistor here, and a voltage still same -2, right?
All right.
However, why do we need that? I'm telling you. When the JFET build for the amplifier, then you get a sideway here, AC signal. The capacitor here, we already know from bipolar, DC blocking, AC coupling. So that's why you get the AC here, then you get AC here, correct?
Right.
Okay, now, when you try to working on AC, all of the power, DC power, must be drowned. You see, they drowned it here. Okay? If they drowned it here, if you don't have a resistor here, sideways will be go to the ground. Cannot do it. That they just prove for you. Why do we need that resistor? Without that resistor, AC signal will be go to the ground. Cannot working. Okay?
So it's to prevent the AC to prevent the AC signal from going to ground.
Exactly.
Okay.
The thing is, when you go into the AC, on VDC must be rounded. See? AC round. Okay. Now, let's see. Next one. One of the most common way to bias JFET cell buyer. Okay. Cell buyer. You don't see any voltage here. You see that? Only a single power supply is used. Okay, that means only in here. The drain supply voltage VDD. And they asking you a graphic. That means for the cell bias, you will be asking for that graphic here. Okay, they given to you to solve the problem. In this case, okay, VGS equal -4, IDSS equal 10 milliamp. Okay, so for this cell buyer, they have no power supply connect to the gate. Okay, so that's why they asking for a graphic. That means they have to given the picture. That one before you can solve the problem. So normally, if you go up to the engineering level, then you can need to do a calculation with the graphic. Okay. However, technician, if you're reading on of the technician textbook, they not try to using the graphic. Okay. So on that one, circuitry here, you don't have a power applied. Okay. VGG here. And they still not working. They still working. Okay. Now, the next one, voltage divider. You already get along with voltage divider. Okay. And you get that a VG. Okay, VDD, VD, VN. And you already know, if you want to calculate the VG, that's a divider. You take VDD times R2, divide R1 plus R2. Okay? And from the gate to the source, you get a diode, plus and minus 0.7. That will be 0.7 volt. Okay? Since the gate source junction has an extremely high resistance, the R1 to R2 voltage divider is practically unloaded. Voltage divider bias is more stable than either gate, that means fixed bias, or cell bias. However, same thing. You will be sorry. Need graphic. Now, let's see. Fixed bias. Okay, they given you this circuitry here. Okay, VGG minus 2 volt. VDD 12 volt. Okay, for the circuit cell, they want to know VGSQ. Okay, IDQ, VDS, VS, VD. Now, again, I explain to you. They can say VGS. However, they want VGSQ. Here, you see that VGS, 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 VGS. However, at a certain point, any point in here, that's what they call a Q point. Okay? Okay, now they given that circuitry, given IDSS, 5 milliamp, VGS up minus 4 volt. First thing, they want to know what VGSQ. Okay, formula, the solution, VGS equal VG minus VS. VG, that means here, minus 2 volt. VS here, 0. That's why you get minus 2 volt. Okay? And if you want to calculate the ID equal IDSS time 1 minus VGS of, okay, and square. I made square here, okay? And that's why they come 1.25 milliamp. Now, you doing the calculation for me, number B, to make sure we get 1.25 milliamp. IDSS time 1 minus VGS over VGS of square. So like the formula, you have to get square. So that's why we are now calculate the IDQ. Who get a 1.25 milliamp, let me know.
Yep, got it.
Okay, good. Then now we go to get the V8. That's easy, right? V8, that means connect to the round 0. And the last one, VD. Okay. VD, that means the voltage here. Basically, they will be equal VDD minus the voltage drop across RD. This is the formula. So make sure you can give it to me right answer 9.25 volt.
$9.25.
Good. Okay. Last one. Remember, the current flow here will be ID, drain current. Current flow here will be IS, source current. They're telling you always ID equal IS. That means the current ID IS will be the same. Okay, cell bias. Normally you don't have to do calculate the cell bias without given a little thing, something else. However, by the way, I given to you basically, they given you this circuitry, and you see they routed here. There will be a cell bias. And cell bias, they asking for the picture graphic here. Okay? That means they given to you IDSS, VGS off. Okay. Now, you want to find out the Q point right here. Okay? Then what they say for JFET and graphic show, they want to know IDQ. That means the current ID right here. Okay? How can we do? First thing, if you want to get a point here, you need to draw the line. You see that? You draw the line, you need to get a one point we call A, and another point will be a B, and you draw the line. When they hit the curve at this point, you go to the right, you get ID. You going down, you get VGS. Okay, we'll see. VGS equal VG minus VS. And they given you VG 0, no VG, minus ID time RS. Okay, VS mean IS times RS. IS, ID the same. So that's why they say minus ID times IS. Now, need to point A, B to draw the load line. First thing, they say, I want point A with ID 0, VGS 0. That's point A. Very simple. The next one, you want point B. Set any ID equal any value. And that value have to be greater than 0, less than VG, V IDSS. So now you can say select ID equal 10 milliamp. That means they the same IDSS. So you get the point, okay? At ID equal 10 milliamp. ID equal 10 milliamp. So now you can calculate the VGS equal minus ID times RS. Okay? So when they select ID 10 milliamp, then VGS equal minus 10 times 0.470. Okay? That means RS value right here. Okay? So you get the point B. Now you get the line A to B. They cut the curve at this point. You go to the left, you get ID. You going down, you get VGS. Okay? If you get a 10, then you can try. Okay? In here they shown for IDQ 4 milliamp. VGS Q minus 2.5 volt. Okay? However, what I'm telling you, you don't have to do that. That's for engineer. Okay? And then, same thing. Okay? Voltage divider using the graphic. So now it would be given you this circuitry here without any help. You cannot. You need a graphic. Okay? And in here, if you go through that, okay, you can see they can calculate the VB right here. Okay? That means the gate right here. Okay, then only one you can do. You have to using graphic they given here. This is a graphic. Okay? And now you need the Q point. That means you have to draw the line. When they hit into the curve right here, then you can get ID and you can get VGS. Okay? Same thing. In order to draw the line, you need 2 points. Okay? 1 point here and 1 point here. Let's see what they're telling you. Okay? Same thing. You need to draw the line. That's what they give to you. Need to draw a line. Point A, ID equal 0. Right here. This on the VDE, which A at this point will be voltage 0. Okay? Okay? Point A set ID 0. then VGS also 0. That's one point. Another point B. Point B, you can set ID equal 10 milliamp. Okay. Then VGS be set ID equal 10. Then VGS equal minus 10 times 0.70 ohm. And you get this point. Draw the line AB. Q point will be the point cut through the curve. You go to the right, you get ID. You going down, you get VGS. Okay?
Hey, Mr. Pham,
Yes, sir.
on point B, is that just a random point? I understand that at point A, you want the voltage to be at the 0 point. That's why you put A at 0. But point B,
No.
It-
Point A here.
yeah, right.
That means ID, VGS 0, right?
right. But I'm saying
Right.
for point
Right.
B,
Point B, then you have to know what ID you want. If you don't want 10, you can get any point here.
in other words, you can make point B whatever you want it.
Right.
Okay, thank you.
But the thing is they already get 10 milliamp here. So that's why they picked that.
Okay, thank you.
Okay. And from that point, okay, you already get the ID. You can calculate the VGS. Okay. VGS. Okay. Equal 10 times. Okay. 0.47. Okay. And this is also example. Now, you can see this is a cell buyer, right? You get only three, okay? Fixed buyer, cell buyer, voltage divider buyer. And we're looking into this circuitry, you must know this is cell buyer. And cell buyer without graphic. That normally you have to do. That means you don't using a graphic to solve the problem. However, what they given to you, they telling you the current ID equal 1 milliamp. See that? They measure the current. They give an ID 1 milliamp. And now they want to calculate VGS. Okay? Q. That means the voltage here. 0. Okay? 0. If you want to calculate the Vs here, Vs will be equal ID times Rs. Okay? And now VGS, basically VGS equal VG minus Vs. VG 0. Vs, okay, 1 volt. So that's why answer will be minus 1 volt. If you want to calculate the VD, okay, VD here will be VDD minus the voltage drop across RD, given you 4.7. And the last one, VDS, that means the difference between the drain and the source equal VD minus Vs. That given you 3.7 volt. Okay, this one just for you. If whoever want to do using graphic, I don't care that. Okay. That one just a problem solving for that. Last one. Voltage divider. Without graphic. So, if without graphic, they must given to you. They given a VD equal 7 volt. Okay? So if VD equals 7 volt, can you calculate the ID? ID. Okay? Equal VDD minus VD divide RD. Okay? After you get ID and you understand IF equal ID on the top. So you know IF, you can calculate the VF equal ID time IF. Okay? You already know VG, right? Equal VDD time R2 R1 plus R2 voltage divider. Okay? So if you know VG, okay, and you already know VS, so VGS, okay, VG minus VF. And the last one, VDS, VD minus VF. You see, that's a very simple, more easy to do calculation. However, we not deal with the graphic. So when they given to you cell bias or voltage divider bias JFET, they will be given you one more information that substitute for using the graphic. Okay, any question up to that point? Okay, if it's not, then I will be stopped at this point. Okay, so also I will be at get a good weekend, and we'll be see you Monday coming.
All right, thank you, Mr.
Thank
Pham.
you.
Have a
Have
good
a good
night.
night.
Good
Thank
night.
you.
Night.
Thank
Welcome.
you. Have a good night.
Good night.